Okay, and this is the part of class where we'll just hang out for 15 seconds or so. Well, I think we can start. Welcome back, everyone. So last week, we took a snow day on Tuesday. It was kind of a rough start, but we convened on Thursday of last week. And we finished most of section 5.1. We're just on the last part of those notes there. So for our first assignment, it's considered officially assigned. It'll be due a week away from today, since we should be able to finish it. For assignment number 2, this is going a little bit further. This due date is now in flux. If the due date stays on January 25th, that means we are thinking we finished 5.2 on Thursday of this week. We need to take a little bit of additional time. I'll just adjust that due date right here as needed. So essentially what will happen in this class, the moment we finish the notes, the due date here will be adjusted, so it's always a 1-week turnaround from the day we completed the content. And that's essentially how each of these assignments are going to work. It says, read section 5.1. If I put this in the description of the assignment as well, we don't necessarily cover everything out of the book. And if there's any time a topic that we're not going to cover directly, I'll mention that, usually in brackets. We're not covering the linear speed, angular speed topics. They're actually pretty interesting, but our course will never, ever talk about them again. Didn't seem like the best use of class time. Then after the reading, these are the exercises out of the textbook that we would solve. So the textbook PDF is up here. You can download it, open it up to that page, and you're doing problems pretty much like a traditional class. If you like, you can do them on paper, hand them in physically, or do them on paper, take pictures of them, email them to me, and that'd be a great way to hand in your assignment as well. Any questions at all, folks, about the assignments or anything along those lines? Okay, well, that's our first assignment. Let's now go to section 5.1, and it's already been quite a while since we did this. We had a holiday. So let's remind ourselves where we were at before we get too far as well. So this is probably one of the bigger starting points for us to begin with. Here we have an idea of positive versus negative angles. So if we rotate in the clockwise direction, we'll consider that to be a negative angle. So that's going to be represented as negative 30 degrees. And we need that arrow to say the directionality of the rotation. And this one, it rotated this far as 180 degrees, then 45 more to give us 225, but positive because of counterclockwise rotation. And what makes it an angle in standard position is all the measurements started on this blue line, the positive x-axis. And that's a habit we'll continue to use as we go through the notes and through the course. Any questions, folks, about the definition of these angles in standard position? Okay, it tells us we can have positive, negative values, and this is how they would plot. Next thing we mentioned is these angles are nice, but our functions are going to take the angles as radian measurement. So we had to come up with a new definition, and this is the idea. If you want to say by how much did something rotate, well, think of this as the initial side. It's rotated all the way here to the terminal side, and this distance could be your thought of what the rotation is. That distance would depend on the radius, so we're going to take...
Yeah, he wanted to eat that. Where'd that go?
Sorry, say again, Kiana?
Yeah.
I was just
Oh, I'm sorry.
No worries, no worries. It happens. So what we did here is we're going to take the arc length, the distance you rotated. The radius is also part of it, so just divide by radius there. So this now tells us how much you rotated. And if it's positive here, it tells us the direction you rotated as well. Any questions at all, folks, about this radian measurement right here? Okay, well, that's the definition. We should try it out right away. So here's our example. It says in a circle of radius 10 meters, an angle theta intercepts an arc length of 43 meters. First thing we should do is just draw that out, and let's start by just drawing the circle. Its radius is 10 meters, so we'll put in, actually want that in blue. Let's put the center here. And here's the radius 10 meters going this way. Now, next it tells us an angle theta intercepts an arc of length 43 meters. And one thing I forgot to put in the notes, but let's put it in here just to make this all a better problem. Let's say here, theta is positive. Doesn't affect the problem other than we're going to get a positive answer, but I want to be definite which way we're rotating on those instructions there. That means we're going in the counterclockwise direction, and the arc length is going to be 43 meters. So that's going to be S itself we're writing in. And although I can't draw this in perfectly, we can actually do a pretty good job just by trying to get an arc length of 43 meters in. Here's what it would look like graphically. Take this length that's 10 meters. Imagine you fit it across the circumference of that circle and bent it as long as you go. Maybe it's a string or something. This would be, to my eye, about 10 meters going that far. That's going to be 20 meters. About 30 meters there. So 10, 20, 30, we're going 43 meters. So about 40, and then 43 right around here is where I would estimate on this. So here's our terminal side. And this is S equals 43 meters. So that's our diagram so far. And sorry, let me just move that 10 meters. It's suddenly in the wrong spot. The thing we want to put into the diagram next is this rotation here to here is our theta. Okay, so that's the sketch of the problem so far. It tells us compute the radian measure of theta. So for this last portion, we'll write theta equals, and you might have noticed you don't really need the diagram, but the more you bring in any kind of drawing like this, the more it really helps, because all of this is pretty visual. Trigonometry is more visual than college algebra by quite a lot. So we'll go over here. Here's our theta. We need to take and write in the arc length first. We rotate way around here, so 43 in arc length. But we had to know how large the radius was, so divide by the radius, 10. And I didn't put in units because we really don't have to. The radius is 10 meters, so 10m. The arc length we put in as 43 is 43 meters. But every time you go to calculate theta in radian measurement, units completely cancel out, and you're just going to get 43 tenths. Radians. So we did it, folks. That's the entire problem. And again, you could have just taken 43, divide by 10, and there's the answer right there. But seeing what's happening visually is and sometimes more important than just running through the formula. So we'll often do this kind of stuff in the notes to try to tie the concepts together. Well, any questions at all, folks, on this answer here? Okay, that's kind of a weird answer. It's an improper fraction, but it is reduced. That's the only thing that we want for this, an exact answer in simplest form. For other answers, you could have called this 4.3 radians. That's also exact. And another thing to mention about this is the radian unit is optional. And work in calculus, engineering, physics, and that kind of stuff, if you're using radians, oftentimes radian as a unit is just completely suppressed. It's just understood you're dealing with radians more often than not. However, let's put in a warning on here. The degree symbol is required. In other words, if you were using degrees, you have to put the degree symbol there to be specific. Otherwise, people might interpret that as a radian measurement, and your answers are not going to be anywhere near close, more often than not. Well, that's the work on this problem here. Any questions or comments so far, folks, before we go to the next content at the moment? Okay, well, to recap, here's where we are so far in the course. We want to define 6 different trigonometric functions, but you have to define the domain before you even talk about those functions. So we started talking about degrees, but the true domain uses radians. So that's all this problem was about, using radian measurement. That now means we have a big conundrum. We need to know how to go back and forth between degree measurement and radian measurement. So we need a conversion factor as well. If we're going to get that conversion factor, practice some conversions, some quick concepts, and that'll be the end of these notes here. So this is what radian measurement looks like. And down below, I have a conversion factor. It just says formula. Radian measure and degree measure are related by these two equations. Pi divided by 180 degrees is 1, and vice versa, 180 degrees divided by pi is also 1. So we have two conversion factors, and you would use this one to convert into radians. The fact that that first equation has degrees in the bottom means degrees would cancel as a unit. And this one is to convert into degrees. Well, they wouldn't really be functions at the moment, but sorry, say again. You could make a function like a multiplicative function, but really they're just going to be things where we would take, say, these degrees right here, or this one right here. So you'd have to be given a problem that looks like this, something in degrees, and you're converting out of it into radians. And so the degrees would cancel on this one right here. It would go just like this pretty much. 270 times pi divided by 180. So it would plug in that way. So it's less of a function and more about you're multiplying a degree measurement by a conversion factor to end up in radians in that sense. Does that make sense with that question there? Awesome, thanks for asking about that. Other questions at the moment? Okay, so those are our conversion factors up here. But I felt before we just take these and trust them, it's a good idea to figure out where do they even come from. If we're going to try to equate radians with degrees, here's the first thing we should do. Let's write down not just any circle, let's write down this circle. X squared plus y squared equals 1. Out of all of the circles, this is the special one. In fact, the trigonometry we're doing is called unit circle trigonometry, and this thing is the unit circle. When we say unit, it's all about that 1 there, which implies a radius 1. Let's plot that unit circle just so we have something we're looking at. So there it is, that's our unit circle. And we do have some good notions of degree measurement. So let's do this rotation here. Let's rotate all the way from here to here. We're going in the positive direction, but anyone volunteer how many degrees that rotation ought to be? Exactly. Exactly 180 or just pi. Let's go 180 degrees right here. So we have 180 degrees. We might decide, well, so what? But here's what else we can do here. Because this is a unit circle, we can say that the circumference is 2 pi times r. But the radius is 1. This turns into 2 pi times 1, giving us a 2 pi. So in other words, radius is 1 on this thing. So the circumference is 2 pi, but the circumference is just a fancy way to say perimeter, right? So when we rotate from here to here, thinking in terms of radians, you have this radian measurement going all the way out from here to here. And you know what? We can calculate that. Like you mentioned, that should just be pi. And here's what we can do. Circumference means going all the way around to get 2 pi. What we plotted is not the whole circumference, that's half of it. So just divide by 2. And the circumference, divide by 2, which is now the arc length S, is just going to be pi. So, well, we can now go take our theta. In radian measurement, theta is going to be the arc length S divide by the radius. But that's what's special about the unit circle. Radian measurement works for any circle, but you might as well pick the simplest one, where R is exactly 1 for radius. That means down here, R turns into a 1. The arc length S, well, it's halfway around the circle of radius, or excuse me, circumference 2 pi, so S is just pi. You might as well plug that in up here just to connect that thought. And so theta is just equal to pi in radians. The unit's optional, but if you want to throw it in, it's often abbreviated as rad for radians, also because it's a great unit, I guess. So now we have two things. We have 180 degrees halfway around the circle, and so is pi radians halfway around the circle. We can equate both of them. 180 degrees is now equal to pi radians, or just pi if you prefer. Then divide by pi or divide by 180, you'll get either this factor or this factor. Let's make that be our last step. I'll divide both sides by 180 degrees to get 1 equals pi divide by 180. And so that's where this conversion factor comes from right here. It's just equating a half rotation, 180 degrees. Interesting facts about circumference of a circle of radius 1 to get pi radians for the actual arc length gets us those two equations for free. So now we can go backwards and forwards from degree measurement into radians where we typically want to be. And if we have to go from radians to degree measurement, we can make that happen. We will do that sometimes in chapter 8 with applications. Well, any questions at all, folks, on the end here?
So it just means like pi is equal to 180.
Exactly. It's
Pi
180
radian
degrees.
is equal to 180. Yeah.
That is correct, yes.
Okay.
Other questions about that so far? Okay, well, we have these two conversion factors. Let's take a quick screenshot. And this is what the homework problems will look like for those portions, that formula there. Just some fast conversions like we mentioned. Let me put it down here. Now let's give this some practice. It says convert each radian measurement to degrees. Also plot the angles on the unit circle. So if you know where negative pi over 6 is, you can start by plotting that. But I think most people would want to convert it first and then plot the result. So for this one, we're starting at negative pi over 6. We write equals to say that this thing is going to turn into negative pi over 6. And we're going to multiply, because we're going into degrees, this one right here, where it goes 180 degrees, divide by pi. So times 180 degrees over pi. And then just simplify from here. So pi will cancel immediately. 6 will go into 18 3 times. So that turns into negative 30 degrees altogether. And when you see pi divided by 6, you're thinking 30 degrees. The fact that it's negative just means it rotated clockwise. Does that make sense to folks on converting this one? Awesome. Well, now that we have that, our goal is to plot this thing. It says to plot it on the unit circle. So when that comes up, I'd probably pretty much just do something like this. Draw a quick circle. It doesn't have to be perfect, but it's easier to draw the circle first, then put some crosshairs on it, and that's easier to center where the XY axis is going to live. When it says plot the angles, from this portion going forward in the notes, we're always assuming the angle has been plotted in standard position. We don't say it repeatedly, it's just now a general assumption. But it being in standard position just means we start with this positive x-axis, rotate by 30 degrees, but in the clockwise direction for that negative sign. Now, if you make it go about like this, to my eye, that looks about like 30 degrees off the x-axis. So here is negative pi over 6, which is equal to negative 30 degrees. What we did, folks, that's our first plot of an angle. As you can observe, it's a pretty rough plot. You don't have to buy extra hardware like a compass and things like that, a protractor and that kind of stuff. As long as you can get it in about the right ballpark, this would be considered full credit. Well, any questions at the moment, folks, with this one?
So can we just like draw an estimate and then do we also need to draw the arrow?
Yes, we
Like-
need this blue
Okay.
arrow out here as well. And yeah, it just has to be estimated. It doesn't
Yeah.
have to be placed.
Like the arrow is in like which direction? Like, so now it's gonna be
Oh, I see
going.
what you're saying. Well, because we put the negative here, we wouldn't
Oh, so
necessarily
you
have,
don't need it. Okay.
but it's not a bad idea to put it in. I'm glad you mentioned that. Thanks for mentioning it. And over the chat, Alex asks, will all the questions be basic multiplications, table numbers? Yes, especially if it were an exam question. It would be very nice arithmetically, something like this. I think I'm going to have some more gnarly stuff with some of these multiplications, but these ones I don't think I would put on exam since it's understood to be closed calculator. Well, other questions at the moment so far, folks? Okay, well, that's one conversion down. Let's try it again. Pi over 4. So negative pi over 6 looks like this. And really the goal with this problem is just to give us a kind of a mental picture of where do all these very, very important angles eventually end up, since we'll need to know that information going forward. So we need to know where pi over 4 is. First thing to do is let's just convert it to degrees where we have pretty good intuition. I'll start by writing pi over 4 equals pi over 4 times. We're using that same conversion factor above, 180 degrees. Exactly. This one's going to come out to 45 degrees exactly. Like before, pi cancels, and the unit we didn't write in, radians, cancel. 4 is going to go into 18. Well, 4 will go into 180 45 times exactly. But just to go with Alex's question, let's suppose this was really an exam problem, and you wrote it out like this. We still have to reduce this thing, so you might divide 2 top and bottom. It's now 90 degrees, divide by 2. Divide by 2 again, and we'll get 45 degrees altogether. So that's where our angle is. Now, if we go to plot this one, (45 degrees is the angle that goes about like that. So here is pi over 4 equaling 45 degrees. And good call. Again, it's a good idea to put the arrows here just because we're still just learning whether the angle is positive versus negative as well. But we did it, folks. That's our second conversion. And that's where pi over 4 ends up. It's on the line y equals x, the 45-degree line here. Well, we'll try going backwards, but any questions at all so far? Okay. Let me take this, and here's our next example. Same stuff like before, but now we're just converting from degrees now back into radians. This one's the problem that we started. But for this problem, it might not be a bad idea to just plot down the angle first. We are starting with degrees, so we usually have better intuition where that would end up. If you're plotting this one, here's probably one way to think about it. Start off with a unit circle like before. And now with the red dot, this would be 0-degree rotation. Right here is where you end up. Nothing happened. We just saw that this is 45 degrees. So if you go this much, 1/4 turn, we're at 90 degrees. 2 turns is 180, and that means 3/4 should be 270 degrees right here. I'll put this last arrow going this way. And here is 180 degrees. We want to convert that down to radians, so that's our work right here that we're going to do. We took this conversion factor, pi divided by 180, multiplied by the degree measurement, and this time, I usually visualize it this way. The degree symbol and the leading 0 has canceled. I effectively just divide everything by 10 degrees. It's going to come out now as 27 pi divided by 18. Still have to reduce this one, but 9 goes into the numerator 3 times and into the denominator twice. So this thing comes out as 3 pi over 2 radians. We didn't put in the unit, but that's okay. The unit is optional for radians, but it is required here for degree measurement. So down below, 180 degrees. we'll now start thinking of that as 3 pi over 2. That sounds unnatural, but after getting through trigonometry, 3 pi over 2,
I think that is
feels more natural.
270 equal to 3 pi over 2.
Oh, sorry, you're right. I'm not sure why I put in 180. That was 270. Thanks for catching that error. Let me put this one in red. That could have been a point deduction if this was a real homework assignment. That is 270 degrees, not 180. Not sure how that snuck in there. Well, that's one conversion in. Thanks again for the support on fixing that typo. Other questions at the moment? Okay, let's try this one more time then. Negative 330 degrees. That one doesn't look super friendly, but we can get through it. So here's our unit circle to start. And now this one's interesting because it's rotating in the negative direction. So that means we're going clockwise. So if we rotate this far, that's negative 90, negative 180. This would be negative 270. And now we need to go 60 degrees more. This is negative 300. And this would be negative 330. Almost silly doing it that way, right? Because if you went this way, all the way around going this way is negative 360. And we just need to go 30 degrees short of that. So our rotation should look about like this. Rotate almost a full complete rotation in the clockwise direction, and that's negative 330 degrees. Next, we'll convert that to a radian measurement. Anyone happen to see what it would be in radians? Exactly. This one's exactly negative 11 sixths pi radians altogether. But let's do that conversion, see how it works out. So we're taking the negative 330 degrees. I usually take this extra step. It's not required, but you'll notice in my notes, I write this out twice. It looks redundant, but it's only so you know what I started with. I started with the negative 330 degrees. Now over here is where my first step is actually going to be at algebraically. We'll multiply this by pi over 180 degrees. And my Microsoft Word got really upset. Let me try to do that slowly for it. Now that we're here, we can do the same kind of cancellation. The 0 and the degree symbol are gone. Also, just like before, 3 will go into 33, negative 11 times, the negative 33. 3 will go into the 18 6 times. So we get negative 11 pi over 6 after reducing, as predicted. Well, we got it, folks. That's the end up for all those conversions. And again, more importantly than the conversions are, where did the radian measurements themselves end up? Like the 3 pi over 2, 11 pi over 6 is probably the most important part of this entire problem. Well, with that done, the next thing I was going to do in the notes is just a couple faster problems that uses some of these ideas all together, a couple additional concepts, and this is really the major portion of the notes that we want to get through. Before we look at those additional concepts, any questions at the moment? Okay, so we've got these last two problems to take a look at. I put a 22 here. I think what happened was this is a screenshot right out of your book, so that's why it looks a little bit odd with the 22 there. And here's how these notes start. This is just a redo of the definition of radian measurement, where you take the arc length, divide by the radius. But what's curious about this as a formula, let's blow that up, is it's a formula with 3 different variables. You can rewrite this in 3 different ways. This is just solved for theta. If you clear the denominator and solve for s, you get a new formula. It's not fundamentally different, but now s is solved for, so we call it an arc length formula in this particular version here. Only because of that s right there. So we need to say, decide just how long is the arc length. This is how you do it. Take the radius, multiply by the angle theta, and you're now in business. So that's what example 6 asks us. Find the arc length s of the diagram below. All we need to do is take Let me try again. S for the arc length. It's going to be equal to R. We have a radius. Here it is, 1 inch. And then it's going to be multiplied by theta. And we do have theta. It's here 150 degrees, but we're actually stopped right at this step. Anyone notice what the problem is at the moment? Exactly. That's kind of the reason I brought this problem to class today. Not that we'll be calculating arc length over and over again. It's a reminder that once we start defining radian measurement, it's used everywhere in even simple formulas like this. It says in a circle of radius r, arc length s is determined by the central angle of radian measure theta. It's given by that formula. In other words, we have to be in radians if we're using this formula. Let's put this as just as a reminder. We require radians. And again, that's just kind of a theme in trigonometry. We use radians a lot. So really our first step on this problem is fix that measurement of 150 degrees. So theta equaling 150 degrees, we'll multiply it by our conversion factor with pi on the top. So pi over 180 degrees. Simplify it as much as possible. Here's my start again. Then we can, divide numerator and denominator by, looks like 3 this time is the greatest common factor. We're going to get 5 pi divided by 6 altogether. So that's our angle measurement, theta, for 150 degrees. No different than 5 pi over 6. So we now can go back to our original problem. Arc length S is equal to the radian measurement. This one is a unit circle, so we're multiplying by 1 inch. Then multiply by theta, 5 pi over 6. And I guess at this stage, we're pretty much done, folks. Nothing really happens here. There's no reduction. We can just call this an arc length of exactly 5 pi over 6. Oop, that's the wrong unit. Let me try again. Inches. And that's where this problem would end. So it's kind of a weird problem in a certain sense. The angle theta is itself the arc length. The only reason that worked out is this one was a unit circle of exactly 1 inch. In any other circle, we couldn't guarantee on that actually happening. Well, that's how to calculate arc length. Any questions, folks, on that computation there? Okay, and there is one last concept before we go to the next set of notes. I asked one question out of both of these concepts, just related things to practice before we move to the next section. This one's called the sector area formula. It's kind of a cool little formula to work with. It says, suppose you don't have an entire circle you want to calculate the area on. So this is some really large circle, but if all you want is the area of this sector, this little wedge of a pizza slice, you could think of it as, then your formula is really just this. 1/2 times your radius squared times the angle. And where this came from is area equals pi times radius squared. If we want the radius of the entire circle altogether, where did the 1/2 come from? We could call this 1/2 times 2 pi radius squared. Let me put a little box in this just to say, this is just an additional topic to go along with this brand new formula we see here. If you look at this formula, in place of 2 pi, oh, I think I have my stuff a little bit mixed up. In place of where 2 pi is, that's my angle theta. But because it's 2 pi, that's the one full entire rotation. Then we'd be taking the area of the entire circle altogether, and it would look just like this. All this changing is, if it's just a sector, say 30 degrees is your rotation, put in 30 degrees right here, and the rest of the formula is the same. You get the right answer each and every time. So any degree measurement, as long as you're from 0 to 2 pi, put it here. If it corresponds to the picture, you're in good shape. So here's how we'll start this one. We need to take our theta. Same problem like before, it's not in radian measurement, so we need to correct it. But 30 degrees is a pretty common one. If you see that that's pi over 6 right away, just throw it in, and that's fine. If you're not sure, here's what the work would look like. Multiply it by pi, divide by 180 degrees. Get that window to go away, there we go. Then the 30 degrees here and the 180 degrees here, we'll have that cancellation. We now have 3 pi over 18, but that's going to reduce to a pi over 6. We got it, folks. The 30 degrees after this work, simplification is just pi over 6 in radians. Let's put rad there just to say that's the unit. Definitely optional though. So once we have that correction there, just doing that conversion, we can go back to this formula and calculate the sector of the area of this sector right here. So area is going to be equal to 1/2. Next portion of the problem is the radius right here, which we square. That'll be the 5 inches in the diagram. So 5 inches squared. Multiply it not by the 30 degrees, but in its radian measurement, pi over 6. And that's our whole thing. Not too much simplification to do here, except, let's see, for what happens in the numerator, it'll be 5 squared times pi times inches squared. So we'll get 25 pi. For the denominator, it's just going to be 2 by 6, so 12. And because of the power 2, and because we know it's an area, this is inches squared altogether. So 25 pi 12ths inches squared is the end area of that sector here. Well, we did it, folks. That's the last bit of the notes, just a couple fast formulas. I don't think I would ask example 7 or example 6 as an exam question. I take that back. Let me be really specific, just because I kind of got that confused. Not on exams. This one's really just for fun, mostly just a fun homework problem, calculating the area of a sector. But I take it back on this one. Sometimes this one can be on an exam. Can be on exams. But if it is on exams, you're just taking this formula, rearranging it. Watch out for anything in degree measurement. I probably wouldn't do that on exam. They're usually pretty direct questions. Well, I want to end these notes with just one additional thing. It's all about learning where their angles are in radian measurement. So I wanted to include a couple sketches here on angles that we should memorize for the purposes of this course. Any questions, folks, before we go to that last concept for these notes?
For those like both example 6 and 7, do we need to calculate like the theta first, or like can we just like put it in the like formula, like with multiply like pi by 180?
Oh, you would have to do this conversion right here first.
Yeah.
So
we cannot do it like in the same problem. Like we have to do it separately. We got to find theta first.
See, no, you could do it in the same line if you like. Yeah, if you throw it out all in one line, I'd be okay with that. Absolutely.
Okay, I got you.
Other questions so far? Okay, well, here's those angles as promised. And here's how we'll title this. Important angles to memorize for trigonometry. Trig is a wonderful shorthand for that. And here's the kind of thought about what we're trying to put down here. These are going to be the angles where we need to be really, really fluent with them. We'll see things like cosine pi over 6 or cosine 3 pi over 2. And we need to be able to output the result of those really, really rapidly. Not just for this class, but for any class that you suspect might use trig. All of the calculus sequence, it's even in linear algebra, it's in weird spots. Your engineering courses are going to use trig a lot. So the more you can memorize these angles, the better you are going to be off in any class that uses trigonometry. It makes a humongous difference. So here's how we'll start. Just one big unit circle. Pretend that's a perfect unit circle. We'll throw some axes on it. Here's the x-axis and the y-axis plotted. And the way I'm going to start plotting these angles are, I'm going to do some scratch over here, and then I'll plot the official angle on the unit circle. First one doesn't need any real introduction. Here's 0 for 0 radians. Then after 0, the unit I want to go in is pi/6. I'm going to go by 30 degrees all the way around that whole circle. So here's the first one at pi/6. All of these are now in radians. And the next natural angle after this would be 2 pi/6. Well, these reduce, and that's one thing that's a little bit weird about it. It might be nice in some sense to leave it as a 2 pi/6. I think that's the question you might have been asking at the start of class. I was possibly not thinking about it right. But for one reason or another, these are reduced, which makes it slightly confusing. 2 pi/6 would be reduced to a pi/3. And a pi/3 is this angle. It's 60 degrees because we went pi/6, which is 30 degrees, twice, to end up right here. I'm trying to color code these as well for patterns that we're going to see to help us with memorization. Okay, so continuing on the pattern, next is 3 pi/3. But that one's just going to reduce down to, or excuse me, sorry, I made a mistake here. It's pi/6, 2 pi/6, then 3 pi/6. I'm just multiplying the numerator by higher and higher integers. 3 pi/6 is the one we wanted there. Sorry for the misstart. That one will reduce to a pi/2, which is this measurement here. So for 90 degrees, going all the way up, terminating right here, we get pi/2 radians. So I have these in black. Certain angles are going to be in blue. Some of them will be in green. And I'm missing all the 45-degree angles. We'll put those in last. Okay, so we were at 3 pi/6. Next one is going to be at 4 pi/6. And it reduces to one of the pi/2s. This one's going to be 2 pi over 3 after reduction. 2 pi/3 goes right about here. So next step on our adventure is 5 pi/6. The 5 pi/6 is special. That's one that doesn't reduce. We're just going to draw it right in. So pi/6 went here, and 5 pi/6 is going to be right here. It's a reflection from one end to the other about the y-axis. So going here to here is pi/6. And let me see if I can fix this axis real quick. I drew it just a little too long. There we go. So after the 5 pi/6, we get 6 pi/6. And that one will reduce definitely to a pi. We knew where pi was. Pi is the half rotation, 180 degrees, ending right there. And as this continues, oh, I did forget to put something in here. That was a 6 pi/6. As this continues, you're going to start to see some pretty interesting patterns from pi/3 to 2 pi/3. Well, pi/6 to, sorry, I'm having trouble copying these in. 5 pi/6 to here. Let me highlight that in yellow. I need to drink more coffee before class, I think. Had trouble copying that in. That one's a 5 pi/6, not a 6 pi/6 or not a pi/6. 5 of them. Then we went to pi. Then after that is 7 pi/6. 7 pi/6 won't reduce, and it's this one going off 30 degrees more than the pi angle. So here is 7 pi/6. Let me take off that yellow now that we have some more correct ones. But notice the pattern going here to here. It's 5 of them to 6 pi/6 to 7 pi/6. Let's continue to add. Next, we're up to 8 pi/6. This is one of the kind of annoying ones that's going to reduce on us, but not too bad. Divide by 2, top and bottom, and you'll get 4 pi over 3. So that's going to be right here, 30 degrees more. So here's our 4 pi over 3. Back to 8 pi/6. The next multiple of pi/6 would be 9 pi over 6. This one reduces to a 3 pi divided by 2 after dividing numerator denominator by 3. So one thing to note is pi over 2's are either up here or way down there. Here's 1 pi over 2 and down below. If you ever see 3 pi over 2, you'll pull coordinates from right here, and that's going to be your sine and cosine, just knowing what the coordinates are after doing the rotation. We're just about done, folks. One last quadrant to go. After 9 pi over 6, we're up to 10 pi over 6. This one reduces, involving a pi over 3 in a denominator. Let's see, we'll divide by 2 on this one to get 5 pi divided by 3. So 5 pi over 3 is this one. And let's see, at 10 pi over 6, the next one will be 11 pi over 6. That's the one that does not reduce. And 11 pi over 6, well, that one's 30 degrees away from the full rotation. So we'll be about right here for 11 pi over 6. And we could do even one last rotation. It was important to know that right here is a 0 radian rotation. Let's put it in a comma because there are infinitely different ways to describe this terminal point right here. You could rotate not at all, or you could do a full rotation. If you did that, you'd go from 11 pi over 6 up to 12 pi over 6, reduce, and we get 2 pi. So right at this location, full rotation is at 2 pi. And this whole game can continue forever. There's loads of ways to describe all these. But notice the angles in blue, your pi over 6s, they're always close to the x-axis. Also notice your angles in green, these ones involving pi over 3, they're always close to your y-axis. It goes pi over 3, 2 pi over 3, below 4 to 5 pi over 3. So there's lots of weird patterns here. And here's the last bit of angles. There just was no interesting way to describe them, but they're the 45-degree angles. This one is pi over 4 that we converted earlier in the notes. Let me control Z that, pi over 4 definitely. If you add pi over 4 to itself, that'd be 2 pi over 4, that's just pi over 2. This one would be 3 pi over 4. The pi over 4s are nice because they go right in the middle of every one of the quadrants, and you're literally just counting them out. This one is going to be 3 pi over 4. They go by odds. So pi over 4 to 3 pi over 4. Add 45 degrees to that, you're here. 4 pi over 4, reducing to pi. At 45 degrees, you're here, and that one's 5 pi over 4. So let's finish off these last ones in purple. This is 5 pi over 4. And this last one, following the same game, is 7 pi over 4. So these are the angles that we ought to memorize for the purposes of trigonometry. It looks like a lot. The more you stare at this, the more you're going to see there are strong patterns here. We're going to be using them quite often. And here's just a short preview of what we need this for. We need coordinates on every single one of these. Say, for example, the coordinates of this point go root 2 over 2, comma, root 2 over 2. That means we'll say in the next notes, cosine at pi over 4 is the first coordinate, and sine at pi over 4 is the second coordinate. So we need the angles, their locations, and the coordinates of all those terminal points. But we'll go over those in very, very excruciating detail when we come to section 5.2. Well, any last questions or comments, folks, on this diagram here or any other work we did?
Do we just need to know them in radians or in degrees too? But we can easily convert it actually.
More important than degrees. So I would probably personally say learn them in the radian mode first.
Mhm.
And as far as degrees, they would be less important, I'd say. Other questions at the moment?
No, thank you.
You betcha. Well, have a great night, folks. This is my last class for the night, so if you do have questions, you can hang her out, and I'll be happy to help out. Otherwise, drive safe, and I'll see you all on Thursday. Yeah. Sorry, say again? Yeah, I wasn't understanding what you were mentioning earlier, but yeah, that's pretty much what's going on. And you know, the only reason we do 5 or 6s is because sine at 5 or 12 is not a nice number. But sine at 5 or 6 is a nice 1/2. That's the only reason we're not dealing with the 12s. Thanks, folks.
But like, symbols like, you write out inch, do we have to write out inch?
Let me double check. I think I did say something about the units. Let's see. I think the only thing I'm being picky on is if it's degrees, we need to use the degree symbol. So I'm not gonna be worried about inches or inches squared or that kind of stuff as much. No, I think you could put that in. That'd be just fine for your unit on inches. Yeah, I wouldn't be too picky on that. Sorry, say again? Yeah, gotcha. Yeah, that'd be just fine for inches, the hash or the quote symbol. Yep, you betcha.